Hi everyone. Today our video is going to continue with our discussion on diffraction. Our last video talked about Young's double slit experiment, which is shown over here on the right. Today we're going to talk about the pattern that light makes when it goes through a single slit diffraction. So instead of having two slits that are very close together, we have one slit that is pretty tiny. The light passes through it and it makes a very different diffraction pattern on the screen behind it. Alright, so to understand single slit diffraction, we're going to talk a little bit about a guy named Christian Huygens, who was a Dutch scientist, and he was the first to propose this wave theory of light. And so what he said was that each point on a wave front behaved like a little individual wavelet. And so if we look at this moment, right, if this is the wave that's propagating this way to the right, and we look at this moment on the front of that wave source, we can imagine that that little point is going to behave like a wave and do its own little diffraction. So what's happening is that it's spreading out as it passes through whatever opening or through whatever space itself, it will spread out, that little point will. And so what he said is that this new wavefront, or you can think of the wave traveling to the right, of course, but the wavefront is the line that is tangent to all of these little crests that get created from these individual wavefronts. And so if the wave is just traveling straight to the right, then you've got this effect happening. And again, if the wave is like bowing out from an opening or something, you have this effect over here on the right happening, where each one of these little points on the wavefront will in turn create a little tiny crest of a diffraction, right? It's going to spread out from its point. And so that effect is essentially what makes diffraction patterns happen. Can you come back? Thank you. Okay. The single slit is shown here in this graphic, and so we have our wavefront just like I described, and each one of these little points along the wavefront will diffract out from the slit here and create its own little wavefront happening. And so what you get is that they end up overlapping and they interfere with each other. So even though you don't have two openings, you don't have those double slits, you're still going to have a diffraction pattern, because essentially the wavefronts are interfering with neighboring wavefronts, or wavefronts that are close to them. So if you look at this second graphic here, the waves that are traveling, or the wavefronts that are traveling completely straight forward, they all travel the same distance to the screen, and so they all arrive together in phase, and they will interfere constructively to produce what's called the central maximum. So if we come back here to this graphic, you can see immediately the difference between the two diffraction patterns is that the single slit diffraction has this super large central maximum, whereas over here on the double slit you really don't get that happening. And then as you spread outward, it looks like the maxima get smaller almost, and as you go out from the center, but it's characterized by this super large central maxima. So that is being created because the waves that are traveling right through the center of this slit, the ones that aren't going out to the side and going out left or right, but the ones that are traveling directly straight to the screen, they all interfere together constructively because they're all traveling the same distance, and they all have the same angle, which essentially is 0. And so you get that really large, bright light right in the middle. Alright, so what's happening on the edges is a little bit more complicated, but what you have going on is you have a bunch of wavefronts, let's say, that are going upward at an angle, or they could be going downward at an angle, whatever. But if you look at the difference between two of these waves, let's use 1 and 2 for the purposes of this example. You look at the difference between wavefront 1 and wavefront 2, and if I were to draw a little triangle that shows the difference between the two of them, I would get a path length here, right? I would get a change in R difference. This means that wavelength 2 is traveling this much further than wavelength 1 to hit the same point on the screen. So just like before, if this change in wavelength is a half, or if this path length is a half of a wavelength, then you've got destructive interference. If that path is a whole wavelength, then you have constructive interference, just like before. So when we look at a single slit diffraction formula, when we're trying to calculate the locations of our lights on the screen, really what we are looking at when we look at that is the location of the dark patches. So the formula looks very similar to the one that we used for double slit, but now whenever we solve for it, we are solving not for the locations of the bright fringes, but for the locations of the dark fringes. So that becomes super important. So don't think that, don't get that confused whenever you start to do some math for single and double slit. And this should be P, I'm sorry. But we have A sine theta equals P times lambda, where lambda is, of course, the wavelength of our light. Now instead of M, we have P, and P stands for the order of the dark fringes. So notice that there is no zero order dark fringe because we have that super large maxima right in the middle, right? So on either side of that maxima will be our first order fringe. And then the second one out from that will be our second order, and then our third out will be our third order. So again, this is talking about the location of the dark fringes, not of the light. So here's a little picture. If you had to draw the wavefront, you guys might have seen this in your simulation the other day. But here we have, let me get a pencil color that can actually show up. Here we have our single slit over here. It has a width of A, and as it travels through, we have some light that doesn't bend left or right or up or down, and it travels straight to the screen. And so we get a super large central maxima. And then the light that diffracts out to the side, if the difference in the wavelength between two wavefronts is half of a wavelength, you get, ooh, that should have pointed to this, destructive, right? But if the path difference is a multiple of a wavelength, you get a light region. So here, this is our width of our central maximum, which is an important thing to know. We're going to do a little question on that in a second. And then we have our orders. Order 1, order 2, order 1, order 2. And remember that this is describing where the dark patches are, not where the light patches are. So if we wanted to, much like we did before with our double slit, figure out where in relationship to our central maxima are our dark positions, we could use this relationship. Now remember that for double slit it looked really familiar. It was y equals m lambda L over d. But now that we're dealing with just a single slit and we've got dark order fringes, we're going to use a little bit different letters so that nobody gets confused. So this pattern is symmetrical, right? So the width of the central maximum here is 2, and that should be 2 times y1. And I'm going to write that on the next screen because I think I wrote it over there for you guys. So let me go there. Okay, yeah, I did. All right, so this single slit diffraction, it's dominated by this large central maximum. So the width of it is defined, like I said before, as the distance between the two P1 minima. So if I just find the distance between this guy and this guy, oh, I'm in white, sorry, you can't see that. If I find the distance between the P1 and this P1, then I'll have my width of my central maxima. So I can do that with a relationship that tells me that the width is equal to 2 times y1. And what is y? Well, y is on the previous slide, but y is p lambda L over a. But when P is 1, then Y is just lambda L over A. So the width is 2 lambda L over A. If I wanted to figure out the size of that, that would be my relationship. So it goes a little bit against common sense because a narrower slit actually causes a wider diffraction pattern. You would think it would be the opposite, that a larger slit would create a larger central maxima, but that is not the case. It is the opposite. Okay, so let's do an example problem. Light from a helium-neon laser passes through a narrow slit seen on the screen 2 meters behind the slit. The first minimum in the diffraction pattern is 1.2 centimeters from the middle. How wide is the slit? So we have a couple of givens, 6.633 nanometers. The L, or our distance to our screen, is 2. And then the first minima in the diffraction pattern is 1.2 centimeters from the middle of the central maxima. So that's our Y1, 0.012 meters from the center maximum. So how wide is our slit? So I'm sorry, how wide is this slit? So we're looking for A. So this is our situation. Our Y is 0.012. Our order is first, so that's just 1. Our lambda is 6.33 times 10 to the negative 7th, and I just converted that real quick. And the length is 2. And we're trying to find A. So we can rearrange all of that, and we should get 0.11 millimeters is our distance, or our A, our width of our slit. This is pretty typical of these slits that create diffraction patterns. So a little conceptual question for you guys on the last slide. Okay, so here you have 2 single slit diffraction patterns. The distance between the slit and the viewing screen is the same in both cases. Which of the following could be true? I'll let you guys pause it if you need to answer that question. Think about it for a little bit. But the best answer choice here, we've got 2 diffraction patterns. That one on the second one, we have a much wider central maximum. So remember that width is equal to 2 lambda L over A. So this guy is much bigger than this guy. So which one of these conditions could possibly fulfill that? Well, definitely B, right? Because we can see that the width of our central maximum is directly proportional to the wavelength. So if I increase the wavelength, that should make my diffraction pattern, or my central maximum, become larger. And then when we look through all of our other answer choices, we see that C is also a viable answer choice, because the wavelengths could be the same for both, but the slit width could be different. And in this case, remember, it's counterintuitive. The bigger the slit, the smaller the central maximum. So in this case, A1 must be larger than the slit opening for wavelength 2. And that's all I have for you guys today. I will see you all tomorrow.